Section 4.9, Antiderivatives. Two topics today. Topic 1, the notation for an antiderivative. Topic 2, examples of antiderivatives. Have a review first. Review number 1, if derivative of some function bf is little f, then we say that the bf is an antiderivative of the little f. This is the definition of an antiderivative. Review number 2, why we need to study antiderivatives? It is because antiderivatives play an important role in the computation of integrals due to this formula. To compute an integral, we need to find one antiderivative of the function little f. Then this integral is equal to antiderivative bf evaluate at the point B minus bf evaluate at the point A. Review number 3. Given a function, how to find all its antiderivatives? 2 steps. Step 1, find one particular antiderivative of the given function. Then step 2, all the antiderivatives of the given function are the particular antiderivative plus an arbitrary number c. A particular antiderivative plus an arbitrary number, we call it the most general antiderivative of the given function f. Okay, now we turn to topic 1, the notation of one antiderivative. The notation of one derivative is either this pi notation or this d over dx notation. These 2 notations are popular notations for derivatives. For one antiderivative, the notation is either bf or this integral notation. This notation is very close to the integral notation, but without the point A or the point B. Why we borrow an integral notation to denote an antiderivative? Because we want to emphasize that antiderivatives play a role in the computation of integrals. By this notation, by this integral notation, okay, we mean the most general antiderivative of little f, the function little f. It means that by this notation, we mean particular antiderivative plus an arbitrary number c. Now we have 2 integrals, this one and this one. Okay. Now we give names to these 2 integrals. We call the integral without a or b the indefinite integral of the function little f, and the integral with a and b the definite integral of function f. Indefinite integral is antiderivative, so indefinite integral is a function. Definite integral is the area of a region, so definite integral is a number. So you should be able to tell the difference. Indefinite integral is antiderivative. Definite integral is area of a region. Now, topic number 2, examples of antiderivatives. Example 1, find the most general antiderivative of each of the following functions. The most general antiderivative means one particular antiderivative plus an arbitrary number C. Okay, now part A, find the most general antiderivative of 1 over x. That is, we need to compute this integral. For 1 over x, one particular antiderivative is natural log. Derivative on natural log is 1 over x. Therefore, this integral is natural log of x plus arbitrary number C. Part B. One antiderivative for this function is x to 1 over 9. Derivative on x to 1 over 9 is this function. Therefore, the indefinite integral of the given function is x to 1 over 9, this particular antiderivative, plus arbitrary number C. Now, part C. Find integral of the function psi of 3x. Now, this time, it is not so straightforward to tell one antiderivative of this function. Okay, now let me make some tries. Okay, make some tries. We know that sine, antiderivative is cosine. Derivative on cosine is negative sine. Multiply this equation by negative 1, then we get negative cosine derivative is sine. But we are looking for antiderivative of psi of 3x rather than of psi of x. Now, let me make a second try. Now, this time, I try negative cosine of 3x. By chain rule, negative cosine of 3x derivative is 3 times psi of 3x. Move the number 3 to the left side, then we get derivative on this function is psi of 3x. This is a particular antiderivative of psi of 3x. So, the indefinite integral of the given function is this particular antiderivative plus arbitrary number C. Part D. Find the indefinite integral of this function. To find one particular antiderivative of the given function, we make the following 2 tries. We first try arctangent. By formula, derivative of arctangent is 1 over 1 plus x squared. This function is close to the given function. Now, the second try. Try arctangent of 10 times x. By chain rule, derivative of this function is this. Now, I move the constant 10 to the left-hand side. Then I get derivative of this function is this function. This is the given function. So, this function is one particular antiderivative of the given function. Therefore, the indefinite integral of the given function is this particular antiderivative plus arbitrary number c. Now, part E. The function in part E is this function. Yeah, we need to find the most general antiderivative of this function, or we need to find indefinite integral of this function. Also, we make two tries to find one particular antiderivative of this function. The first try, we try r psi. Derivative of r psi is this function, close to this function. Now, multiply this equation by 11. Multiply this equation by 11. Then we get that derivative of this function is the given function. So therefore, indefinite integral of the given function is this particular antiderivative plus arbitrary number c. Example 2. Find all the functions g that satisfy this equation. Derivative of g is this function. So g is an antiderivative of this function. Now, to answer the question, we compute the indefinite integral of this function. So g is indefinite integral of the right-hand side of the equation. For integrals, we also have summation formula and subtraction formula, and the formula for scalar times a function. But for integrals, we don't have product formula. We don't have quotient formula. Okay, now by summation formula, I can split this big integral into a sum of two smaller integrals. Constant 4 times a function. Constant can be moved outside the integral. Then I get this. The first integral here is easy to tell. Antiderivative of psi is negative cosine. But the second integral, difficult to compute. To compute the second integral, I write the function in terms of powers. I split this fraction into a difference of two fractions. Then in the first term, I can cancel 1x. In the second term, I can cancel 1 square root of x. Then we get this. Now 1 over square root of x, I can write it into a power. The power is x to negative 1/2. Now replace this function by this function. Then we get this equation. Okay, now I apply the difference formula to this integral. Then I get this difference. 2 constant, I move it out. Then I get this. Now, it's easy to tell the antiderivatives of these three integrals. Psi antiderivative is negative cosine. X to the 4th antiderivative is a 1 over 5 times x to the 5th. X to negative 1/2 antiderivative is 2 times x to 1/2. Don't forget to add an arbitrary constant c. Okay. Now simplify this. then we get the answer. Yeah. This is all the functions G that satisfy this equation, where C arbitrary. So this function essentially is many functions. Example 3. Find a function f that satisfies these two conditions. To answer this question, I first find all the possible function f that satisfy condition 1. That is, find all the possible functions that satisfy this equation. Second derivative of function f is equal to this polynomial. So first derivative of the function f is indefinite integral of this polynomial. Indefinite integral means antiderivative. Now, by the summation and subtraction formulas, I can split this integral into 3 smaller integrals. It's easy to find the antiderivative for each of these 3 integrals. 12x squared antiderivative is 4x to the third. It's easy to verify this. Take derivative on this guy, then we get 12x squared. 6x antiderivative is a 3x squared. Constant 4 antiderivative is a 4x. Then add an arbitrary constant c. This is all the possible first derivative that satisfy condition 1. To recover function f from this equation, derivative is this polynomial. So function f is indefinite integral of this polynomial. By summation and subtraction formulas, I can write this integral into a summation and subtraction and difference of these 4 smaller integrals. 4x to the antiderivative is a 4x to the 4th. 3x squared antiderivative is x to the third. 4x antiderivative is 2x squared. And constant c antiderivative is c times x. Then add an arbitrary constant d. I use d because I have used c here. C and d, they are arbitrary constants and they are independent to each other. This is all the possible functions that satisfy this condition, condition 1. There are, because c and d arbitrary, so there are infinitely many such functions. Now from these infinitely many functions, I pick one that satisfies the second condition, condition 2. Condition 2 has 2 equations. The first equation says that when x is 0, function value should be 4. Now I plug in 0 in x here. This is function f. Plug in 0 in x here. Set the result to 4. Then I get this equation. From this equation, I get d is 4. The second condition, the second equation in condition 2 is function value at 1 is 1. So plug in 1 in the x here. Set the result to 1 to get this equation. D is 4. D is 4. So solve this equation for C. We get C is -3. Okay, now C -3. D is 4. So the function that satisfies these two conditions is this function. Example 4. A particle moves in a straight line and has acceleration given by this equation. Initially, when time is 0, the velocity of the particle is -6 cm per second, and the position of the particle is 9 cm. Now, from this information, find the position function of the particle. Because derivative on velocity is acceleration, so we have velocity is an antiderivative of acceleration. In other words, derivative is indefinite integral of acceleration. Acceleration in this example is 6t plus 4. Then we compute this integral to get velocity. This is a summation formula. 6t antiderivative is 3t squared. 4 antiderivative is 4t. Then add an arbitrary constant c. This is all the possible velocities. Now let me determine c so that the velocity satisfies the initial condition. When time is 0, initially velocity is -6. So plug in 0 in t. Set the result to -6. Then we get this equation. Therefore, we have c is -6. So the velocity that satisfies this initial condition is this velocity. On the other hand, we know that derivative on position is velocity. That is, position is antiderivative of velocity. So position is integral, indefinite integral of velocity. Now plug in this function in velocity, then we get this equation. Split this integral into a sum, a difference, and then find antiderivative for each of the three integrals. Then we get S is this. D, arbitrary constant. I use D here because I have used C here. Okay. Now to determine D so that this initial condition is satisfied, I plug in 0 in t here. Set the result equal to 9. Then I get this equation. So therefore, d is equal to 9. D is 9. So therefore, the desired position function is this function.